Ellie here from Academy. Now, Greenwood have done quite a few solar farms and some big BESS storage systems, and in doing those projects we discovered some interesting stuff about soil temperatures and soil resistivity and its impact on cables and how they derate. And this particular presentation is all about that. So what we're going to cover is the different cables, how they derate according to the temperature of the soil, the depth of bury, and also the consistency of the soil. And we're talking about direct buried cable here in relation to solar farms. All right, let's get stuck into it. Welcome to Cable Derating and Soil Temperatures on Solar Farms Best Practices. This training is aimed at designers and installers working on utility-scale PV who need to avoid cable overheating and nuisance constraints when burying AC and DC cables across Australia's very different ground conditions. Now, we are talking Australia specifically. We are referencing Australian New Zealand standards AS 3008, AS 3000 as well. But the theories and the practices are applicable to any country in the world. We're going to identify and understand potential problems with cable sizing. We're going to understand how soil temperature and soil thermal resistivity changes current carrying capacity, the CCC, of buried cables. We're going to use AS NZ 3008 tables and correction factors with Appendix A worked examples as a pattern to size derate cables for direct buried, but we're not going to really look at in-conduit layouts. And we're going to develop a methodical step-by-step process. Let's get into it. And now here's a picture of one of the solar farms we recently completed in New South Wales, a little under 5 megawatt on the AC side and a little over 5 meg on the DC side. Underground cables overheat if soil conditions are underestimated. Solar farms in cooler southern soils versus hotter northern soils, you're talking about completely different outcomes. Imagine a scenario where you're doing a solar farm in Victoria and you've got soil temperatures ranging from 15 to maybe a max of 25, and you do a particular design. Now imagine if you rinse and repeat and take that same design and go up into the northern states, specifically Queensland, where the soil temperatures can range between 25 and 35 plus degrees. Are you going to get the same kind of cable current carrying capacity? The answer is no, and that's what we're going to be really talking about. Australia shows large spatial and seasonal soil temperature swings, north and interior much hotter, coasts cooler, and the south being much milder. In southern Australia, the soil temperature can range between 15 and 25 degrees C, but in the northern interior regions, the soil temperature can be 25 to 35 degrees plus centigrade. And also, there's going to be within-site variability due to depth, shading, and moisture. So it's not only the soil temperature that plays a role in the current carrying capacity of the cable. It's also the kind of soil we're talking about and its moisture content and how deep the cables are actually buried. Thermal resistivity. This particular measure defines heat transfer from the cable to soil. Soil thermal resistivity is basically how bad the soil is at getting rid of heat from your cable. Now, anyone who's done any electrical work, especially in renewable energy, whether it's on the roof or a ground mount system, knows cable derating, AS 3008, very important because what it comes down to is the ability of the cable to dissipate the heat as effectively as possible. And it does that through the insulation. It's the key is the insulation. And if you've got a situation where the cable is direct buried, you're talking about no airflow effectively around these cables at all and a thermal mass contributing to its ability or inability to get rid of heat effectively. The higher the rating, the hotter your buried cable will run for the same current. In other words, the hotter the cable, the lower the current carrying capacity. Now, native soils, these can vary from 0.9 to 2.5 when it comes to thermal resistivity. Engineered backfills, on the other hand, usually have a value of less or equal to 0.7. The higher the rating, The higher the cable temperature, the reduced CCC. Now, I mentioned engineered backfills. What we're talking about is a trenching situation where the native soil has been taken away and disposed of, and then as an option, an engineered backfill has been put in because it has a lower thermal resistivity. Obviously, this comes with that caveat of doing your appropriate cost-benefit analysis. Standards, touch points. We're obviously going to be referencing the Australian NZS Standard 3008, and we're looking at the current carrying capacity tables, correction factors, and we're looking at Appendix A worked examples. And you can see an example here, Table 12, buried direct, column 13, in copper. Obviously, copper is going to have a different current carrying capacity than aluminium, and we're going to be looking at that. Anyone involved in any electrical work really must become accustomed to understanding these standards. 3008 is the one that seems to be most misunderstood, especially when it comes to cable derating. And of course, there's AS3000, which is the master standard. Standard touch points, IEEE 442, soil thermal resistivity testing methods. Let's look at an example where we need a current of 450 amps for our DC feeder, and we have selected 2-core 240mm XLPE X90 with a copper conductor. So we've determined on this particular case study solar farm that we'll need 450 amps, and the cable we've gone to is a 240mm squared XLPE X90. Let's see what it looks like from a current carrying capacity. We're going to direct bury it at a depth of 800mm. Now, the CCC of 630 amps, this comes from AS3008, Table 11, Column 23, buried direct, and it assumes a thermal resistivity of 1.2 with a 25-degree soil temperature. We have a soil factor of 0.92, and we have a soil temperature factor of 1. And a depth factor of 0.96, and this is based on the 800mm selected. So effectively, what these figures mean is that you've got your original 630 amps based on 25 degrees with a thermal resistivity of 1.2 at a certain buried depth. And from there, if you increase any of those factors, you're going to get a reduced current carrying capacity, and we're going to look at that. So the adjusted current carrying capacity is 630 amps, the original figure, times 0.92, which is a soil factor, times 1, which is a soil temperature factor of 1 in this case at 25 degrees C, times 0.96, which is the derating factor based on an 800mm burial depth, and we've got the final result is 556 amps. So that's all good. So we're all good. We're well over the 450 amps that we need for this particular cable run. So let's look at some other variations. All good. But now we have a project in Queensland. So how are we going to go with the 2-core 240mm XLPE X90 buried direct, but this time with a thermal resistivity of 1.6 and a soil temp that is now at 35 degrees. So we've increased our thermal resistivity of the soil. We've increased the soil temperature. How much of an effect is that going to have on the actual current carrying capacity of that same 240mm XLPE cable? Let's find out. We're talking the same depth at 800mm, but a soil temp increase and soil resistivity increase as well. Let's have a look. So we've got a soil factor now of 0.81. Okay. We got a soil temperature factor. It was 1, now it's 0.91, and that's because of the thermal resistivity of 1.6. The depth factor of 0.96 based on the 800mm selected stays the same because we haven't changed the depth of bury. So the adjusted current carrying capacity is now 630 amps times 0.81 times 0.91 times 0.96, and it equals 446 amps. Uh-oh, that's a fail. So we've effectively failed. The question is, can we vary any of these? We can't vary the soil temperature, and we're not really going to vary the depth of bury. So the only thing possibly we could do is bring in some engineered backfill, and we'll look at that later on. What if we use a different kind of cable? Say 240 mil, 2-core sheath, RH110, or a similar high temperature cable. It has a higher current carrying capacity of 665 amps according to AS 3008, Table 12, Column 13, buried direct, assuming a thermal resistivity of 1.2 with a soil temperature of 25 degrees C. So the adjusted current carrying capacity is 665 times 0.81 times 0.91 times 0.96, and that's 470 amps. Phew, all good. So we got a success here, and just by changing the kind of cable, we're still staying with a 240 mil squared conductor, but we're going to a higher temperature cable. In other words, the insulation is better at getting rid of that excess heat. Hence its current carrying capacity. I always have trouble saying that. CCC is better than a 90 mil rated, than a 90 degree rated cable. I'll get it right eventually. Solution options. Now there are a few options that the designer can look at, but they will also need to do a cost-benefit analysis as well. Can we reduce the bury depth? If allowed, how much will this help? Maybe we're going to look at a trenchless system, or use an engineered backfill with a thermal resistivity value of less than or equal 0.7. So this is the question that the designer has to work out well before anything starts on site. The pros and cons of a trenchless system. You're looking at, well, no trench, so no OH&S considerations there in regards to trenching, but you are talking about cable that is directly exposed to the sun, and how is that cable going to be accommodated, and then you have to look at the longevity of the particular cable that you've selected versus, yes, we're still going to dig a trench, we're still going to put the cable at 0.8 direct buried, but now we're going to bring in an engineered backfill. What are the costs involved there? So let's look at this scenario where only the temperature differs. So we're looking at the first column and we're looking at cable description. I've got three options. Well, actually, they're all the same. It's 240 mil cable, 2-core, right? The same insulation type and conductor temperature rating. You've got your base current carrying capacity of 630 amp. You've got your P factor at 1.6 with the resulting soil resistivity factor of 0.81. Soil temperature of 15 degrees. Soil temperature factor of 1.06. It's actually gone up, right? Depth of bury 0.8. Depth factor 0.96. You've got an adjusted current carrying capacity in amps of 519. So you can see the soil temperature decrease from, say, 25 degrees. Even though you've got a thermal resistivity of 1.6, I can still, in a 15 degree soil temperature at 800 mil, I can still use that cable because I'm well above the 450 amps required. Now, what about the next option where we go 25 mil, 1.8, and that's 490. So you're looking at 490 amps at 25 degrees at 1.6. So we're above. We're still above. If we look at the last option at 35 degrees, soil temperature factor of 0.91, depth of bury 0.8, but look at that, adjusted CCC in amps, 446. So we're below. So you can see at 35 degrees, as mentioned before, all the other factors being the same, you can't use this cable. You're off by, according to the calculations, 4 amps. Let's look at another example where the depth of bury differs. So we're starting off with a thermal resistivity factor of 1.6. We've got the same temperature across the board, 25, 25, 25, right? Depth of bury 0.5, depth factor 1, so we got 510. We're not going to bury at 0.5, but I just want to show you how the depth of bury determines, all other things being equal, the current carrying capacity of the cable. Let's look at the next example. 0.8, 490 as we saw before. If we go down to 1.2, you can see there's a drop from 490 down to 469. That's a drop of 21 amps because we've buried it from 0.8 to 1.2 meters. So you can see that correlation there. This is the thing you have to get your head around. When it comes to current carrying capacity, it's all about heat dissipation, how quickly the cable can get rid of heat. When you're burying direct, in no particular order, how deep you go, the soil temperature, the thermal resistivity of that soil, and moisture and all those other things come into play as well. Now, in this example, only the thermal resistivity factor differs. Everything else stays the same. So we're looking at an engineered backfill of 0.7 thermal resistivity, and look at the adjusted carrying capacity in amps, 689 amps. And we're looking at depth of bury at 800 mil. Soil temp 25. The next example, we're going to 1.2, 556. We go to 2.5. This is truly horrible soil from a thermal resistivity perspective. And you're looking at 423 amps. Soil thermal resistivity really plays quite a proportionally large role in reducing or increasing the current carrying capacity depending on that level. So the lower the soil thermal resistivity, the better the actual current carrying capacity of the cable, all other things being equal. Let's look at some best and worst case scenarios. So in the first row, under the heading, you're looking at the same base. You're looking at a P factor of 0.7. You're looking at a soil temperature of 15 and a depth of bury at 0.5. So that cable can cope with 761 amps. So if we go to the next option with a thermal resistivity of 1.2, and a 25 degree soil temperature and a 800 mil bury depth, 556 amps, all good. Let's go to the last one. Absolutely ridiculous soil, 2.5 thermal resistivity. You're talking a 35 degree soil temperature. You're talking about a 1.2 meter bury, and look at what it does to the current carrying capacity after all that derating, 369 amps. So hopefully you're starting to get an understanding of that intrinsic relationship between all these factors. Now we're going to look at a step-by-step process that you should go through ideally to assess what's needed for these solar farms from a cabling and burying direct or in conduit configuration. Let's get stuck into it. Step 1, define the scope and the electrical topology. So first things first. So look at the block size, export voltage, and the inverter arrangements. Is it a central or string? In most cases with a solar farm, you're looking at a central inverter, but not always. 2, look at the maximum feeder currents, both AC and DC. Take into consideration the redundancy needs and future capacity. That's really important. Maybe you're going to augment to this solar farm. Maybe it's going to double in size, or it's going to go up by 50% depending. There may be some battery energy storage coming in there. What's that going to look like from a cabling perspective? You must take that into consideration in the early days on this project or on your project. Number 3, obviously look at the grid and the NMI requirements and point of connection constraints. Now, step 2, gather site and climate intelligence. So we're talking about local ground temperatures at burial depth and also the seasonal highs and lows. More seasonal highs, that's where you should be doing your calculations. The soil type, the moisture regime, the groundwater, the salinity and the corrosivity. Environmental and land access, easements, sensitive areas, flood fire risk. Step 3, plan the geotechnical investigations. Obviously, geotech is needed not only for your trenching, but it also for your piles, whether they're going to be pile driven in, whether you're going to be using concrete foundations, whether you're going to be using an earth screw approach or a superfoot kind of approach, you'll still need to do a geotech. Many a project has started after not enough geotech investigation, only to discover gigantic floaters in the form of basalt that are very costly to remove and very timely, very costly time-wise in regards to the project moving forward. So really make sure that your geotech guys or the company that you employ do the right job, do a thorough investigation, make sure they take lots of core samples. Line source problem in situ and lab verification of the candidate backfills. The deliverables have to be the soil temp profile, the thermal resistivity, moisture, density targets, backfill recommendations if required. Step 4, choose installation approach. Direct buried in engineered backfill, best heat path civil work. Maybe use a conduit and duct bank, protection and maintainability, watch for thermal penalties. Take into consideration shared versus segregated trenches, mutual heating versus the civil cost. Like all things on all projects, it really comes down to a cost-benefit analysis. For example, using an engineered backfill may seem expensive, but maybe it's the least expensive of any other option. At the end of the day, you cannot change the existing soil temperature and its thermal resistivity, so that may mean that you bring in engineered soil, or you go trenchless and you get those cables above the ground. You just have to do the proper analysis. Step 5, routing and trench design. So you have to take into consideration corridors, crossings, separation, AC/DC, comms, water, gas. Really important too, what kind of machinery is going to be driving through the solar farm after you've finished. You know, there may be a case it's just maintenance vehicles, or you might be bringing on large 300-ton cranes in the future. You just don't know. So you must take this into consideration in regards to existing infrastructure there and all the infrastructure you're actually putting in on site. Typical depth warnings, tape, markers, mechanical protection, pulling geometry, bend radii, drum locations, winch access. In other words, make sure you plan for good vehicle access and determine exactly where your cable drums are going and where your cable pulling is going as well, and who's actually involved in that process and their experience level as well, really important. Step 6, cable and conduit selection. What we're talking about here is a selection between copper and aluminium, and the qualities of that insulation, both in 90, 110 and 120 degree variations, and also is insulation termite and rodent proof, very, very important in a direct bury configuration. The configuration, is it going to be SDI, 2-core, 3-core, trefoil versus flat for singles? You may be putting in conduit as well. We're not really covering the conduit side of things in this particular presentation, but these are the things you have to work out well before you get to site. Conduit size and fill, less than or equal allowed percentage, number per conduit, spare ducts policy. So obviously with cable and conduit, it is all about friction. You're talking about multiple cables in conduit. You're talking about the friction of the cables against each other. You're talking about friction of the cables against the internal walls of the conduit, how many bends there are, what's the allowable space, what is best practice, and these things, again, have to be worked out well before you get to site. Step 7, thermal strategy. No calculations here. So you design for worst case, highest ground temperature and highest thermal resistivity from the geotech. Decide early, engineered thermal backfill versus upsizing versus more parallel cables. Plan spacing, segregation to manage grouping and mutual heating. Step 8, earthing and bonding. Now, remember, obviously, you have to take this into consideration as well. Earthing on solar farms is an art in itself for those who understand it. So spend the time to plan your earthing and bonding schedule carefully. So we're talking about a soil resistivity survey, electrode type, depth, whether it's ring, grid, rods, bonding of metallic conduits if used, cable screen, sheaths and structures, corrosion control, materials, coating, and lightning interface. Now, lightning protection is a course in itself, which we're not covering here, but we will be covering it in the future very soon, specifically for solar farms. Step 9, standards, approvals, and interfaces. So the Australian standards NZS 3008, cable selection and derating. We're looking also at AS NZS 3000, that's the installation rules. Also take a look at AS NZS 4777.1 2024 inverter installation requirements and DNSP utility specs. Step 10, construction, QA and hold points. Backfill recipe, placement and compaction QA, moisture control. Conduit spacing, depth, markers, photo evidence before backfill. Cable ID, per phase, core markers, test plans agreed before works. Step 11, commissioning and acceptance. Pre-energisation, insulation, sheath tests, continuity, phasing, earth resistance. Thermal imaging under initial load, verify alarms and limits. As-built drawings, red lines, O&M handover package. Step 12, operations and heat event playbook. So you're talking about monitoring feeder temps, loads, soil moisture if instrumented. Heat wave actions, curtailment thresholds, inspection triggers, periodic earthing tests, trench subsidence and corrosion checks. Continuing on with step 12, we're assuming a generic thermal resistivity or cool soil temperatures from other sites. Yeah, but you know what they say about assumptions. Overgrouping in shared trenches or overfilled conduits, missing earthing upgrades in hot, dry, high resistivity soils, skipping backfill QA, losing the performance you paid for. One-page checklist, geotech request checklist, routing and trench checklist, construction QA hold point list, and commissioning and acceptance checklist. Now, your references obviously is AS NZS 3008, AS NZS 3000, and AS NZS 4777.1 2024, and of course, utility and DNSP specific requirements. That's really important. Make sure you've got a good relationship with the DNSP. Thanks for watching, and if you want to see anything else on commercial solar farms, energy storage, flywheels, please let us know. Don't forget to like, comment and subscribe to this channel and also to Greenwood Academy, and see you in the next one.